This is Greg Troutwine with Maritime Reporter TV, and we're very pleased to be joined today by Jonas Moberg, head of Newbuildings, Gotland Company, and Michael Welch, Siemens Energy, to discuss sustainable ship design and building, and specifically the world's first large-scale multi-fuel hydrogen-ready catamaran.
My name is Jonas Moberg, and I'm head of Newbuildings at the Gotland Company. I'm the responsible for the Gotland Horizon X project, which is now ordered and under a shipbuilding contract. I've also been responsible for developing the Horizon series, we call it. So we have some other designs up the sleeve as well. I'm a naval architect, and I've been working a lot with our new building projects through the years in our company, and also as a surveyor at the Swedish Transport Agency, and I'm also a captain of high-speed vessels.
Michael Welch, I'm based in the UK. I've been playing with gas turbines for a very long time now, 35 years. Started off as an applications engineer, actually designing small power plant and compression plant. I moved into sales and business development, where I started looking into energy efficiency and new applications for gas turbines. The new applications morphed into marine. Energy efficiency morphed into decarbonisation. I'm currently working as a dual role tech lead for some of our fuel flexibility and carbon capture activities, and business development still for the marine activities.
Jonas, can you provide a by-the-numbers look at Gotland Company today?
Our company is an old company. It's from 1865, and the core business is passenger service, ferry service from the mainland of Sweden to the island of Gotland. But we have expanded our areas of operation to the Copenhagen-Oslo route, and we have also a cruise vessel operating in the Baltics. So you could say three major operational areas. We use three ships in the service to the island of Gotland, and that is high-speed RoPax ferries, but they are conventional. So they run at 28.5 knots, which is quite high for a conventional vessel, with both passengers and cars and goods, and also dangerous cargo and everything, and we could run all year round. The Copenhagen-Oslo route is pretty much similar, a little bit slower speed, but it serves both passengers and goods and cars. And then the cruise vessel is a pure cruise one, without any cargo, operating between Stockholm and Mariehamn in Finland. So that's the core business, and then our company invests in energy, especially a little bit green energy, and we also invest in tourism industry, real estates, and within the company, Gotland Tech Development, we look at novel technologies in order to get the maritime industry through this transition period of the coming 20 years.
You know, we're obviously here to discuss specifically that vessel. So can either or both of you really discuss the big overview of the vessel, the size, the speed, the capacity, the projected timeline for delivery? And really what I'm getting at is any additional technical or equipment specifics that really make this vessel stand out.
I think I could start, and the main size of the vessel is 130 meters long, so that is one of the longest catamarans in the world. The width is 30.5 meters, and the gross tonnage is 18,300. So it's quite a big ship. In the 90s, Stena, they built the HSS 1500 that was slightly bigger gross tonnage, but it was shorter, so our is longer. It's a 30-knot ship, So it's a high-speed catamaran, but we have, let's say, optimized the speed for our service. And the aim for using this ship is in the ferry service between the mainland of Sweden and the island of Gotland. So we're under a contract with the Swedish government, and that requires a certain timetable. We're talking 1,500 passengers and 400 cars as the capacity of the ship. And delivery is planned in summer 2028. And we have, on top of the pure size of this vessel, is a really novel engine arrangement, which Michael can tell you all about. But is a gas turbine in combined cycle with steam turbine. So we have a waste heat recovery system where we actually enhance the efficiency quite much. By putting everything in combination, we could enhance the efficiency up to almost 50%. So on par with the best diesel engines.
It is quite unique this time. I think this is the first time anybody's tried this. We have the gas turbines driving steerable water jets through a 2-gearbox arrangement. So we're stepping the gas turbine speed down from 9,500 RPM to 1,800, and then 1,800 down to about 400 for the water jets. There's a little power takeoff generator on that 1,800 to 400 RPM gearbox as well. So that's generating the hotel load for the Gotland Horizon X vessel. And then, as Jonas said, we're recovering the waste heat from the gas turbine exhaust to produce high pressure steam. And then the steam turbine itself is driving a booster water jet. And that's how we get the high speed. So we've got about close to 36 megawatts of power going through the water jets on when everything's at full load.
Can you give some guidance specifically on the vessel, the route, and the technology that really made hydrogen ready the choice for this?
Yeah, well, it's as always, you have to start somewhere. Yep. And we started to think about our operation, different routes we have, and also the contract with the government. That in fact today everybody seems to appreciate the service, and especially the timetable, which is 3 hours typically, time to go the long distance, 80 nautical miles with a high capacity, and that is something we want to preserve. So we wanted to, you could say, mitigate the environmental impact while keeping that high level of service and the high speed. It requires quite high speed. It requires almost 30 knots, 28.5 knots. So that was the starting point. You could say the capacity and to look, okay, could we do something cleaner? So we had a vision in 2009 where we decided to go for gas. So said and done, we developed and ordered 2 new RoPax ferries, dual fuel ships that could operate on liquefied natural gas and also, of course, blending in biogas. And those were built in 2018 and 19, and they are operating now on the service. So first step, without having the infrastructure in place for fueling, we took a bold decision and we built the ships, and they're operating fine, and we are learning that. So we came to the next question. Okay, what's next? What's the next generation? And then we started to think about, of course, batteries. But we have this issue. This type of traffic requires huge energy, and in order to have batteries to store that energy, it requires a lot of weight. That's not good when you run at high speed. And also charging the batteries was almost impossible. So we ended up with looking for a cleaner fuel. And let's say on the top shelf, you have the hydrogen. If you could achieve something, you could run on hydrogen, you have very low exhaust gases. If you do it in a fuel cell, it's only vapor coming out. If you do it in a combustion engine, then it's almost only vapor coming out. So, and that's also, hydrogen is also a component if you design other fuels. So we're thinking that if you could use it directly, that's the most efficient way. So that was driving us to search for could we use hydrogen, and how could we make use of the hydrogen? And then we ended up with a gas turbine could be suitable to run on a high portion of hydrogen. But we wanted to go all the way. We want to go 100% hydrogen. And that's where we found the perfect match with Siemens and Michael. So
the hydrogen story is one that we've been working on for quite some time. Obviously, Siemens Energy, our main markets are the industrial power generation markets, utility markets, and oil and gas. And governments in Europe in particular have been encouraging people to look at hydrogen as the fuel for onshore power generation, your big power plant, as a means of decarbonising grids and backing up intermittent renewables. It's very difficult to do the development work and testing that's necessary on the large utility scale gas turbines. They just consume far too much hydrogen for a start. So we made the decision that the test model for hydrogen was going to be our SGT-400 gas turbine. It's a good size at 13 megawatts, and it consumes a realistic amount of hydrogen that you could actually procure in the market for all the testing purposes. And so Jonas had been reading about the EU-funded HyFlex Power project, where we'd been running an engine in a paper mill in France on hydrogen, and the discussions went from there. And it just so happened that the SGT-400 is also the machine that we think is the best gas turbine fit that we have for marine applications. So the two just came together very, very nicely.
Can you just give us a little more specifically on the Siemens Energy SGT-400 gas turbine?
In the early 1990s, we recognized that there was a gap in the market for a machine in sort of the 11 to 15 megawatt power range in our traditional markets of oil and gas and power generation or cogeneration. So we designed and launched the SGT-400 in 1997. It's what we call a twin shaft gas turbine, so as a free power turbine, which means we can vary the speed of whatever the unit is driving, which is great for pumps and compressors. Also turns out to be good for propellers and water jets. But we can also run at a fixed speed for a generator set as well. Being twin shaft, it also has the advantage that it makes it very, very compact, because the exhaust now comes either out the side or out of the roof of the gas turbine package. So it fits very, very nicely into a solution like a ship, where the boiler can be sat above the turbine. It leaves a very compact installation. The beauty of the SGT-400 is, because it was designed for cogeneration, it still has quite a high exhaust temperature, because in cogeneration you want lots of steam production, because it's steam that the customer is looking for, not electricity. So when it comes to the combined cycle, that high exhaust temperature means you have a very high combined cycle efficiency for a machine of this size as well, which is why we're getting close to 50% with the steam turbine. We also made the decision that this was going to be the first gas turbine we did that had the dry low NOx combustors on as standard. So there's 25 years now experience running on natural gas and LNGs, diesels, and we've now developed that combustor as well to be able to run on methanol, and then a variation of that combustor will run on LNG and hydrogen, as Jonas has alluded to. Market-wise, we're now close to 500 units sold in the market, 7 million operating hours accumulated across the fleet. Although this would be the first maritime ship application for us for the SGT-400, it's very, very similar to the offshore experience we've got on FPSOs and oil and gas platforms, where we've got about 80 units since 2000. So there's a lot of experience that we've been able to carry across. And in fact, with one or two exceptions on the fire and gas and controls, the package is actually, that's going on to the Gotlandsbolaget project, is actually the same as we'd use as a mechanical driver on offshore applications.
What are the specific, or are there specific design and technology challenges to bringing this vessel to fruition as compared to a traditional diesel-fueled vessel?
I think first it's important to mention what Michael said. They already started the process of getting these gas turbines approved for marine use. And that's step number one. I mean, as a naval architect, I could find some good engines shoreside, but they're not suitable for going on a ship that moves back and forth. So that's the first step, actually, the approval. And that was already ongoing. And I think that was a key. The combined cycle, without that, the efficiency would have not been good enough for us. A lot of, especially high-speed vessels, were built in the 90s with gas turbines, so that's nothing new. Beautiful ships, but the efficiency, fuel efficiency, is so poor, so in the range of 35% something. And that would not be happening for us. So that's the first two steps. I think it's very important to understand that the Siemens SGT-400, that it was under development for 100% hydrogen, that caught our interest. But at the end of the day, in order to push the button and sign a contract, it has to be approved for marine use. So that is the first one. The efficiency-wise, going combined cycle, that was necessary today to have on board. And that puts us under a lot of challenge design-wise. Once that is, let's say, established, then comes, let's say, the challenge to fine-tune this. You have everything like gas turbine is very fuel flexible, but all equipment around it, you need to think about the fuel handling system. So you can, even if it is flexible, you can use any fuel almost. But if you don't have the fuel handling system for it, there is no flexibility, so to say. So you have to choose a little bit. We designed the ship for 100% hydrogen. And we're thinking that if we have hydrogen, large-scale hydrogen there, we could also have as a plan B, a backup. We could use the same fuel handling system for methane. Because if you could handle the small atoms of molecules of hydrogen, you could use the same system for methane. But here and now, we don't have large-scale hydrogen ready. Available. So we had to think, if we're signing this now, we have to go conventional for a period of time and then transform the ship into hydrogen. So we're building the ship with LNG tanks and diesel tanks. So we could run them on existing fuel, we could mix it with biogas, and then in the future, when hydrogen arrangements and infrastructure and production are in place, then we could switch to hydrogen. So fuel handling, the key, and the surrounding systems, like the exhaust boiler, needs to cope with whatever you get out from the turbine. So yeah, that's important. The filling, I mean, today, if I pick up the phone, I call Shell Oil or someone and say, I need 30 tons of diesel. Yeah, just pinpoint where we should come with the truck. But if you're talking hydrogen, if it is liquefied or if it is pressurized, you need a complete arrangement in order to get it on board. So that is such a challenge, but it's not impossible, we have seen. So I would say those. If we go into details, I would say the high pressure of the fuel side going or required into the gas turbine creates some problems on the LNG side, creates boil-off gas we need to handle, and to evaporate makes it difficult. But that's maybe too detailed.
I just echo what Jonas said, that there's two key challenges. Off skid for us, it's making sure that the fuel has been stored and handled correctly so that we get it in the condition that we want it. And then on the skid, the fuel system that gets it from the skid edge into the turbine itself. That's quite challenging for hydrogen. We have some interesting discussions with DNV to have when that time comes. But then, yeah, the big challenge on the turbine itself is on the combustor, making sure that it's burning the fuel in the right place with the right levels of emissions and at the right temperatures. Natural gas or LNG and diesel, well used to. Hydrogen, that's been a very interesting development program that's taken 10 plus years.
Can you provide a by the numbers look at the project in total? And really what I'm getting at is trying to get some insight to the additional costs that are incurred in the design, the build, and the operation of this vessel with this variety of fuels and or the hydrogen specific fuel supply.
Well, maybe I could give you a number, and that is 25%. So if we, let's say, go out there, it's always difficult to compare apples and apples, but we could purchase a ship with this capacity a lot cheaper than this ship actually, and that's important to know, that under competition, if we go head to head with some other competitor, then of course that is not possible. But if we put it into our system, where we have a seasonal traffic with a high season in summertime, where the capacity, let's say, is a bottleneck, where we actually could introduce this ship as part of the entire system that runs all year round, we could actually live with this higher cost, because in the proportion it's not that much, and then we could consider all the coming increased costs on the fuel side. Then it's a little bit of what you believe in the future, but for sure this multi-fuel product we have is during its lifetime now of, let's say, 25 years, we have the opportunity to switch gradually between the fuels, so we don't have to, let's say, scrap the ship or sell it and build a new one. So we're better prepared, and over the life cycle, it will be, let's say, a plus minus zero event. But who knows about the fuel costs? If we would have gone on a fuel cell version, we would have been more locked in. So the flexibility here, I think, is key the coming 10, 15, 20, maybe 20 years. And we have seen it when we went to the first LNG ships, that the pendulum swings, first everybody's running for LNG, and then suddenly that's out of the question. And then step by step, it comes into play, and we have kept our compass as an extension of our owners and the board that take these decisions. and try to think realistically at the same time as we think visionary. So a combination there is that's our experience, I think, from being a ship owner, building ships for many years, and we do it to use them many times their entire life. Then we could see it in a long time perspective, and then it makes sense. Short term asset play, not good, but long term, and that's where we are.
As you look at this process from the start to the date, can you offer any lessons learned?
I think one key, if you come from the operation side, I mean, ship owner or ship operator, many people know about gas turbines. They know that the efficiency, as soon as you leave the 100% power output, efficiency goes down. So it's poor from the beginning, and it becomes worse. And normally, I mean, for 25 years of operation, you don't really know what will be your service speed. It will vary, etc. Once we went for the combined cycle arrangement, and it's a bulky one, unfortunately, so it's tricky to design. But once we took that step, we saw that the efficiency actually is almost flat, from 100% down to 50% and lower. So suddenly, at least I had in the backbone that if you go gas turbine in lower power output, that's really not a good idea. But that is one lesson learned for me, actually. And that's interesting for all the ship owners, I think, that you have a quite flat efficiency, which is really good over the spectrum of 100% down to something, 40% maybe.